In the last video, we looked at how you could use the symbol of the particle to determine the quark composition, and that was for composite particles. We also looked at fundamental particles and how they sit outside this. They don't contain quarks. Now, just because those fundamental particles don't contain quarks, that doesn't mean that they're always stable. And some particles, such as muons and tauons, which aren't on this list, they can decay into electrons. That means that fundamental particles can change from one type to another. And the force that does that is the weak nuclear force. Now, the weak nuclear force is difficult to visualize as a force, and there are various jokes out there about how is it really a force. There's a lovely 𝗟𝗶හි𝗸𝘀 cartoon. I don't own the copyright to that, so you'll have to look it up. Type in 𝗟𝗶හි𝗸𝘀 weak nuclear force into Google and have a look at that cartoon. It's good fun. The weak nuclear force is the one that's difficult to explain, but it doesn't need to be if you understand the nature of force. Remember, a force multiplied by time is an impulse. An impulse is a change in momentum. Now, you can change momentum by changing a particle's velocity, or you can change momentum by changing a particle's mass. And that's what the weak nuclear force does. The weak nuclear force acts to change mass into energy or vice versa. And it does that by changing these fundamental particles. Quarks can change from one type to another. Leptons can change from one type to another. And the only force that can change fundamental particles is the weak nuclear force. Now, there are three types of bosons, the W+, the W-, they tend to be put together as the same type of boson, and the third type, which is the Z0 boson. Z0 boson is uncharged, does the same sort of thing, but it's uncharged. We can leave that off for now because it's not on A-level specifications. But the W+ and W- boson is. And what's interesting about the W+ and W- boson is they are also electrically charged, which means they exchange virtual photons with all other charged particles as well. Very interesting. They are very, very massive. The comparison I've used here, this is a particle, a W boson, that can be emitted by a fundamental particle, but the particle, the W boson, has a mass comparable to the mass of a silicon atom. That seems almost unbelievable, that you could have, for example, a muon emitting a particle which has more mass than a silicon atom. The muon doesn't have that much mass. So where does that mass come from? Where does that energy come from? Well, Heisenberg's uncertainty principle helps us here. It's not true that you can't create and destroy energy. Not really. What's true is that over a period of time, the amount of energy in a system, an adiabatic system, remains constant. And the shorter that period of time is, the more you can see fluctuations in that amount of energy. Now, the half-life of these W bosons is tiny. They do not have a very long range at all because they've got such a small half-life. But that means that they can have tremendous mass. They can be very energetic. The universe can lend 30 giga-electron-volts per c squared, as long as it gets it back in time. And it's a very small amount of time that they live for. So this diagram here is a pretty typical example of a particle interaction diagram. It's not quite a Feynman diagram, remember, but it'll do for now. A neutron is a composite particle. It contains two down quarks and an up quark. And we can look at the particle properties of a neutron to figure that out. Neutrons have no strangeness, zero charge, and it has to have three quarks because it's a baryon. So that's up quark, down quark, down quark. Now what will happen here is one of the down quarks will emit a W- boson. The W- boson carries away that -1 elementary unit of charge. So the down quark is transformed into an up quark. Up quarks are a little bit less massive than a down quark. Not by a lot, but they are a little bit less massive. In this interaction, the W- boson is emitted, but the W- boson does not last very long. Very quickly it decays into 2 leptons. Well, I should say 1 lepton and 1 anti-lepton. The W- boson has negative charge, so it decays into an electron and an electron anti-neutrino. Now in doing this, the proton, which has less energy than the neutron, has dropped in energy. We've got less energy afterwards. And that energy has now gone into the electron and the electron antineutrino. Remember how entropy works. The universe is trying to spread energy out as much as it can, and that's what's happening here. In this example, a nucleus that contains more protons than would be stable can become more stable if those protons turned into neutrons. So a proton can turn into a neutron when an up quark emits a W+ boson. The up quark decays into a down quark. Now, although the down quark is more energetic, overall the nucleus will be less energetic, so this is an allowed interaction, as long as it's from a proton-rich nucleus. The W+ boson, with its positive charge, decays into a positron and an electron neutrino. So what's happened in these two examples is the fundamental particle, the elementary particle, which in this case is an up quark and in the previous example was a down quark, has decayed. In doing so, the composite particle has also changed. But that's because of that fundamental particle changing, and that's the work of the weak nuclear force. More exotic particles will also decay in the same way, although it can be a little bit more confusing. For example, a 𝗟𝗶+ particle here, which has strangeness, will decay eventually into a proton because it's a baryon. The strange quark will decay via the weak nuclear force into an up quark. And it does that because it loses -1 elementary charge units. So our strange quark here, which has a charge of -1/3, if we subtract -1 from -1/3, we end up with +2/3, which is the charge of the up quark. And so this W- boson carries away that -1 elementary charge unit. It then decays, and in this occasion, that W- boson decays into two quarks. Well, a quark and an anti-quark. It decays into a down quark and an anti-up quark. Only the weak nuclear force can decay into two different types of quarks. Now, when it does this, the most stable configuration for those 5 quarks that are left over is an up and up and a down forming a proton, and an up and an anti-up forming a pion, a neutral pion, and that neutral pion will go on to decay further. But this isn't the only way that a 𝗟𝗶+ baryon can decay. A 𝗟𝗶+ baryon can decay in other ways as well, and there's a probability of those different decays. Slightly more simple is this example of a �sigma- decaying, when the strange quark decays into an up quark. Remember, up quark is less massive than a strange quark. And the strange quark does so by emitting the W- boson. So that's exactly the same as before. But now this is the configuration of quarks that comes out after the interaction. Now, you may think it's quite difficult to remember all of these possible baryon decays, and of course it is. It's far too difficult to remember. It's hard enough trying to remember all the quark compositions that you can see here. These are the quark compositions of the composite particles for baryons that you might have to remember in the future. There's quite a lot of them, or you could just work it out from the symbols. But trying to remember all those baryon decays, that's much more challenging, especially because there's different possible ways some of these baryons can decay. One of the things you could be asked about is to decide whether a baryon decay is possible or not. We can cover that later. There are fewer mesons to have to learn the quark composition of, but still the same principles apply. You could use logic and understanding of the symbols to figure out what the quark compositions are for mesons. And here I've got the most likely decays for these mesons, and you can see that some of them are very, very likely indeed. For example, the possibility that a positive pion would decay into an anti-muon plus an muon neutrino is almost 100%, but it's not the only possibility. Probability determines what's going to happen, and here are some other possible decays. Far too many to try to memorize. And each of those decays has a diagram accompanying it, and there's no way you'd want to memorize all of those. But you can see all of these problems instead as logic puzzles to solve. Now, I haven't yet mentioned about the decay of leptons. Remember, leptons also exchange these W bosons, and so they can also change. Because they're fundamental particles, they can change by the emission or the absorption of a W boson. Similarly, you could draw particle interaction diagrams for all of these decays if you were motivated and If you're studying A-level physics, you're probably going to have to do that at some point. So in the next video, we're going to talk about some of those conservation rules that you can use to figure out what interactions are possible, what interactions are not possible.